Hello, everybody. Our project is trapping microparticles using ultrasonic waves in flowing water. My name is Jackson Stobart. My teammates are Alex Jagger, Tim Lee, Ashwin Parmar, and Daniel Fisher. So some background information on why we might be trying to use ultrasonic transducers is they're effective in possibly fluid purification and particulate extraction. They can be used to do composition analysis once you retrieve the particles out of the flowing water. And even in biomedical applications, we see them as effective ways of separating maybe bacteria from a sample of blood, so we can get a general idea of how contaminated someone's system might be. So our main objectives or our main requirements for this project were to provide a 40 volt, 2 megahertz signal to a pair of transducers. Now these transducers, as you may be able to see in the yellow CAD design, are to be positioned opposing one another, and they are going to both be pulsing DC signals repeatedly to where they create standing waves in a channel. And as the water flows through the channel, the microparticles will hopefully get trapped in the standing waves, and we'll be able to photograph, extract, and do analysis on the composition of the particles in the fluid. This is also going to be a battery-powered system, so it also needs to be low power and efficient. And we're going to be doing a series of designs to try to create a more efficient trapping technique. I'm going to let Alex Jagger talk to you about the driver circuit design and the details on that.
So for our driver circuit, our input signal is going to be coming from the MSP 430 6047. This is a chip developed by TI for ultrasonic sensing applications. It's actually a low power device, so it works well with our project. And so that's going to be our input signal into two different op amps. One of them will be inverting, one will be not inverting. And basically we'll get 0 to 20 volts amplification out of the non-inverting and 0 to negative 20 out of the inverting. And once we put those two outputs across our two transducers, we'll get a peak-to-peak of 40 volts, 2 megahertz signal, which will allow us to create the standing waves in order to trap particles.
So once we're done implementing our driver circuit and powering our transducers, we're going to focus our efforts onto designing the most efficient housing mechanism. So we're going to look at variables like the angle of the transducer, the channel width, how far apart the transducers are, and the flow rate to try to maximize the efficiency of the system itself. So we've seen from previous research that about 15% efficiency is where they seem to maximize that. So we hope by the end of our project we'll be able to achieve that efficiency. And hopefully also we want to implement a user interface that can connect to your computer wirelessly and offer you feedback and data from your system. That'll wrap everything up. If you have any questions for us.
Yeah, I've got a question. Can you tailor this to a specific molecular weight? I mean, like if you're looking for a particular molecular weight, can you scale it to that?
So originally our design and the research we previewed, the transducer's frequency is set to trap things on 100 to 500 micron. So we haven't really looked at the density or the weight of the particulate, so it'll come into play of what we actually use, and we'll test those in our analysis.
The reason that I'm asking is because if you could scale something like this up to maybe hundreds of thousands of gallons a day, you're looking at maybe the possibility of extracting precious metal from seawater or precious metal from an ore, a crushed ore. So, again, maybe that's something that's too far down the line, but you guys might want to think about that for a scale up.
Thank you. We didn't consider that.
So what about this design needs an MSP 430, basically any kind of microcontroller? If all you're doing is generating a single frequency standing wave at a particular voltage, then you can use much cheaper, less amount of circuitry to do that.
Right, okay, so the reason we're using it is this is already implemented for time of flight measurements to get flow rate. So they have a lot of applications where this is already being used. So our hope is to maintain that functionality and also add the ability to trap particles and then do some sort of composition analysis or possibly even extraction at that point. So we want to maintain the time of flight capabilities as well.
Okay, and what are you doing with that specific, you're measuring the flow rate through it as you're doing the
Exactly.
standing wave?
Yes.
And then the follow-up question of that is, how sensitive is this approach to the container versus the electronics? Which is the more difficult engineering problem? Is in getting an exacting 1% tolerance housing, or?
I would
some
guess
way?
housing. Honestly, we haven't gotten far enough to answer that for sure. We've been focusing on developing the driver circuit so far this semester. But the different housing apparatuses that we've tested do get drastically different, basically amplitude received by the other transducers, so that has a big effect on its ability to function. But we'll be getting more into that next semester. Thank you.
All right, let's thank the team.